When a model gives a wrong answer, it does not feel embarrassed, and it does not magically know what went wrong. The first thing training needs is a ruler, something that measures how far this answer is from what we wanted. That ruler is called a loss function. A simple way to think about it is a wrongness score for the model. It does not only say correct or incorrect, turns the mistake into a number that can be compared. Suppose the answer is cat, but the model gives cat only 30% probability. That is not just a small slip. The loss function says, you were not confident enough in the correct answer, so this mistake deserves a larger penalty. For a number prediction, imagine the real house price is 3 million, and the model guesses 2.8 million. That is still wrong, but it is closer than guessing 1 million, so the loss should usually be smaller. This is why different tasks use different loss functions. Care about different kinds of mistakes. Continuous numbers, a common choice is squared error. The intuition is simple: measure the gap, then punish bigger gaps more strongly. Why square the gap? Because small misses stay relatively gentle, while large misses become much more expensive. Classification, a common choice is cross entropy. Cares about how much probability the model gives to the correct class. If the correct class is cat, and the model gives cat 90% probability, the loss is small. If it gives cat only 10% probability, the loss becomes much larger, even before we talk about the final label. Large language model pre-training uses the same basic idea. The model sees the previous text and predicts the next token. If the next token should be apple, but the model assigns apple very low probability, the loss goes up. So training data is like a huge pile of tiny questions with answers. For each question, the model receives a loss score. After a batch of questions, we average those scores. That gives us the loss for this training step. Now the model knows how wrong it was. But knowing that is not enough. The harder question is, how should the model change? It may have billions of parameters, so random guessing is impossible. Think of the model as a giant machine full of tiny knobs. Each parameter is one knob that can slightly change the output. Training means adjusting those knobs so that the loss number moves downward. This is where gradient descent enters. It answers a practical question. Which way should we move to reduce the loss? Start with only one knob. Turning it right makes the loss bigger, and turning it left makes the loss smaller. The next move is obvious. You should turn it left, but only a little. A huge turn may jump past the best point. A gradient tells us which direction points uphill and how steep that uphill direction is. The gradient points uphill, then to make the loss go down, we move in the opposite direction. That is the core of gradient descent. It is not magic. It is walking downhill on a map of errors. The update formula on screen can be read in plain English. The new parameter equals the old parameter minus a small step. That small step has two parts. The gradient gives the direction, and the learning rate controls the size of the step. If the learning rate is too small, training crawls. The model may improve, but painfully slowly. If the learning rate is too large, the update can jump over the valley and make a loss worse. So optimization is not just changing parameters aggressively, it is changing them steadily enough to keep moving downhill. Here is a tiny example. The input is 2, the correct answer is 5, and the model currently predicts 2. Prediction is too low. The loss records that gap, and the gradient tells the parameters how to push the output upward. After the update, the model sees another batch, computes loss again, finds gradients again, and updates again. After many rounds, what looks like learning is really a loss curve gradually moving downward. It is a bit like practicing basketball. You miss a shot, notice where it missed, then adjust your wrist and force. If feedback only says wrong but never says left, right, high or low, improvement is much harder. The loss function gives the score. The gradient gives the direction. The learning rate decides how far each step goes. In real deep learning, there may be billions of knobs. Nobody can tune them by hand. Backpropagation sends the loss signal backward through the network and computes how each parameter contributed. So backpropagation is like assigning responsibility, while gradient descent is the actual knob adjustment. But lower loss does not automatically mean the model behaves exactly how humans want. It only means the model is becoming better at the training objective we gave it. If the objective is poorly designed, the model may learn shortcuts instead of becoming genuinely reliable. That is why modern large models also use instruction tuning, preference learning, and safety evaluation after pre-training. Still, the basic loop remains the same. Predict, compute loss, compute gradients, update parameters. In one sentence, the loss function tells AI how far it missed, and gradient descent tells it how to change next. AI does not suddenly wake up smarter. It is slowly pushed toward better answers by many small mathematical corrections. Now compress the whole idea into the smallest possible math example. Imagine the model has one parameter, and the input multiplied by that parameter becomes the output. If the input is 2, the parameter is 0.5, and the target is 5, the model only outputs 1. The loss is clearly large. If we increase that parameter a little, the output rises. In this position, that moves the prediction closer to 5, so the loss goes down. Tells us the parameter should increase here. The gradient is the tool that computes this local direction instead of relying on our intuition. But if the parameter is already too large, the model may output more than 5. In that case, increasing it again would make the loss worse. So the gradient does not always say make the parameter bigger or always say make it smaller. Depends on where we are on the loss surface. In a real neural network, there is not just one parameter. Each parameter asks the same question. The answer for one parameter is its local rate of change. Plain language, it is that parameter's responsibility signal. All those responsibility signals together form the gradient. It is like an arrow on a very high-dimensional error map. Propagation computes those signals efficiently. It is not literally sending pain backward. It is using the computation graph to distribute responsibility layer by layer. The mathematical engine behind this is the chain rule. In human terms, the final error is split backward through every intermediate step that helped create it. If one parameter strongly contributed to the mistake, it receives a stronger update signal. If it barely mattered, its update is smaller. Real training also usually does not inspect the entire dataset for every single update. That would be too expensive, like regrading the whole exam after every correction. Instead, training uses a small batch of examples to estimate the direction. This is the idea behind mini-batch stochastic gradient descent. The mini-batch direction is noisy. It may wobble, but that wobble is not always bad. It can help the model move through flat or awkward regions. That is why a real training curve is rarely a perfectly smooth slide downward. It usually trends down while shaking along the way. You will also hear about training loss and validation loss. Training loss measures performance on practice examples. Validation loss checks new examples. Training loss keeps falling, but validation loss starts getting worse. The model may be memorizing the practice set instead of learning a general pattern. Problem is called overfitting. It is a reminder that a lower loss only matters if it improves the right data, not just the data the model already saw. To reduce overfitting, people use early stopping, regularization, more data, augmentation, and other tricks that stop the model from memorizing fragile details. Optimizers also go beyond plain gradient descent. Adam, for example, remembers recent directions and adapts the step size for different parameters. You can think of Adam as someone who walks with memory. It looks at the current slope, but also remembers the momentum of the last few steps. Even then, the core story is unchanged. We need a loss before we can define a direction, and we need a direction before we can update parameters. So when we say AI knows it is wrong, we mean something precise. The training objective creates a computable error signal from data. And when we say AI learns step by step, we mean thousands or billions of tiny updates push its parameters toward lower loss. Once you understand loss functions and gradient descent, the rest of neural network training becomes much less mysterious.